잘라지는 못하게 있어요? 아, 오케이. 아. Orthogonal matroid or so-called even delta-matroid.
Thank you.
Please.
Thanks for the introduction. Yeah. So as Sangil said, I will talk about the even delta matrix. So orthogonal matrix is the same. I think no one heard about the orthogonal matrix, but I think maybe half or the 1/3 of the audience heard about even delta matrix or delta matrix. And yeah, this is just one of the matrix extension of the matroid, which generalize both basis exchange axiom and the symmetric and some kind of grid algorithm. And I think nobody heard about the tract. Oh no, maybe we heard. So in some lunch seminar we heard about the Matt Baker's talk about the matroid or partial hyperstructure, and in that talk he mentioned about the tract. And tract is some kind of, some generalization of the field. So maybe some of you are familiar with the matroid representation over some field, and tract is some kind of generalization of that. So it is some kind of ring-like structure, but with the usual commutative multiplication, but the sum is very unusual. So I will explain this tract at the end of my talk, and yeah. So let's recap the definition of what is matroid. So a matroid is nothing but a pair with a finite set and some set of the subsets which denoted by this weird B and satisfy this basis exchange axiom. So for any basis, and we have some one element only contained in one basis, then we have another element in the other basis, such that this is also a basis of the matroid. And actually, without this condition, this is the original definition of the matroid defined by Pitney in 1935, and actually this weaker condition is equivalent with this stronger condition. Yeah. So I like, of course, stronger condition, and the rank of the matroid is nothing but the size of the cardinality of any basis. So you can check from this condition. You can easily check that cardinality of the bases are always same. And the circuit of a matroid is just nothing but a minimal subset of the ground set, which is not contained in any basis. So if you're not familiar with the matroid, then it looks weird. So I will give some example, very simple example. So if you consider the graph G, let's assume that this is connected. And then if we collect edge sets of spanning trees, then this is a basis of the matroid. You can easily check. And also the circuit, the set of the circuit of the matroid for this graph, this matroid is, you know what? Circuit of the matroid associated with this graph is just same as the. I know. Yeah, cycles. Of course, you know. And this is one motivation of the matroid, and the other motivation, second motivation, is about, of course, the vector or the vector spaces, because matroid is something like matrix plus suffix OIDs, which means something similar with the matrix. So yeah, of course you need to consider about the vectors. So we have some n vectors in some ambient space. So K means the field, and n is of course positive integer. And now from this, let's construct a matroid. Ground set is nothing but n vectors, and its bases are all maximal independent vectors. So for example, if V1 is something like 0, 1, and second one is 1, 0, 0, 1, and 1, minus 1, then the maximal independent set is V1 and V2, and V2 and V3, and V1, V3, but not V1, V2, V3. And yeah, so we say a matroid is representable over a field K if this M is isomorphic to this kind of matroid. Okay? And for the vectors, you can also understand it as a matrix formula. So if we collect all those vectors as a columns of certain matrix, so let's consider A as m by n matrix, such that its rows are something like this. And let's consider its row equivalence. And R is the length of this matrix, or the length of the spans of these vectors. Then after row equivalence and after some discard some usually it's called rows, then you can get the R by n matrix, and such that some determinant have the non-zero. Determinant of some scarce matrix is non-zero. So we can regard this as another matroid whose bases are the set from 1 to n, such that this means that R subsets of n, determinant of. So I remember that Hyun would say to me that please do not center at the center, but yeah, this condition. This means that this submatrix and this determinant is non-zero is equivalent with the some columns indexed by x is maximally independent. Yeah, this is some examples of the matroid. And now I will explain what is an even delta matroid, which is equivalent with the orthogonal matroid. Maybe yellow is better. Even delta matroid is a pair of the same setting, but it satisfies some another axioms. So for all bases, and so also we choose arbitrary element in the symmetric difference, and we choose another element in the also symmetric difference. Then there is some it satisfies these conditions.
Can you say the two conditions at the same time?
Yeah. Actually, even delta matroid was first defined in this way, but actually this weaker condition is same as the stronger condition, which is proved by Wenzel in early of the 90s.
Does it mean that this is even? Or?
No, even so, delta matroid is a condition. So basis exchanging action without this and this condition. And even means that So one typical example of the even delta matroid is of course matroid, and so you can check that for the even delta matroid, all bases have the same cardinality. So that's the reason why we say this called an even delta matroid. And the matroid all have the same cardinality, and if we drop this condition, then you can check that our basis can be arbitrarily sized and no parity condition. Nice. As I mentioned, one typical example of the even delta matroid is of course matroid, and actually if matroid is just equivalent with the even delta matroid, all whose bases have the same cardinality. Okay. And the second example is also comes from the matrix representation.
Can I ask a question? If both E and F are contained in B2 but not contained in B1, then the B1, the symmetric difference with E and F is
reduced size by 2.
Yeah, then the length function is not well defined.
The length function of this even delta matrix is not defined, but also there is a way to define the rank function, but it's satisfying some weird condition compared to the matroid.
Yes.
Sometimes people say pi sub modular, something, I don't know. I cannot remember exactly what it's named, but there is a way to define the rank function. And okay. So another typical example of the even delta matrix comes from the skew-symmetric matrix. So all diagonals are 0 and something like this, skew-symmetric matrix. And also, let's assume that these rows and columns are indexed by E, finite set. And if we collect all subsets of E such that the principal subdeterminant indexed by X has non-zero determinant, then it forms an even delta matrix, which is proved by Boucher. And yeah. And actually this condition is equivalent with the Fabian of this subdeterminant is non-zero. So this Fabian is I will not define what is Fabian, but Fabian is most useful for the skew-symmetric matrix because of this theorem. So this is theorem by Cayley in 17th century. 70? 80? I mean something like this. Scale of the Fabian is equal to the determinant of the because of that, yeah, this is followed directly. And so, since if we scale any number, then we lose information about each sign. So Fabian has more information than the determinant. So sometimes I will use Fabian rather than the determinant. And yeah, also we say even delta matroid M prime is representable over K if M is isomorphic to this kind of matrix, comes from the determinant, comes from the skew-symmetric matrix, and with some additional operation which called twisting. So if you observe that this condition, then always empty set is contained in this, because we assume that determinant of the 0 by 0 matrix is always 1. And yeah. So, however, in the general setting for the even delta matroid, it is not true. So, because of that, so this notation means that this is in the basis of this. If and only if the symmetric difference between B and X is also in this. So, some trivial condition.
You didn't say what X is. So.
Sorry. X is some subset of the E. Thank you. And yeah. So you may wonder that why I introduced this representation. So one funny lemma is that if we have the matroid M, then this is representable over certain field K in the matroid sense, in the usual sense, which I described it here, is equivalent with the M is representable over K in this even delta matroid sense. So I will give some simple sketch of this. So if we have the matrix representation of the M in the matroid sense, and up to row equivalence, you can assume that this is the first R rows are the identity matrix, and this is remaining. And then after that, you construct some skew-symmetric matrix, which looks like C minus CT. And then what you can observe is, let's index this by X. And you can observe that for any...
What are those empty boxes?
Sorry, this is 0. 0. 0. And then what you can observe is I will denote it as a prime. And determinant of a y. So y is something like r side subsets is equal to the Papian of the a prime x symmetric difference y. Why? So if we observe that here, and this part is identity matrix, right? So this is nothing but the determinant of, same with the determinant of this. And if we observe the x symmetric difference y, then it looks like this. So this is x and this is y. And we know that this is 0 and this is 0 and these are equivalent, this just same with the this. So I mean, if you know the definition of the Papian, then you can easily check that, oh, these are same. So this proves that, oh, for the matroid case, our representation are same. Okay. Up to now, I explained what is even delta matroid and some representation of the matroid, and also even delta matroid. So I will introduce some known result of the representation of the matroid, and also I will explain some known result about the representation of the even delta matroids. So main application of our result is, we can do something on the matroid representation of the even delta matroid. So okay, so for the matroid, so Todd did many things. So first he showed that M is binary. Binary means that it is representable over the binary field. I mean, the field of characteristic 2, if and only it has no U24 minor. So, yeah, U24 is something with 4 ground set, it has size 4, and all its subset, all its bases are the size of 2. And also he did, if M is regular, what it means is it is represented by certain matrix over the real field, such that all its subdeterminant is 0 or plus minus 1. And what he did is, also he finds some minor obstruction, but I will skip. And also he did is, this is regular if and only if it is this matroid is representable over all field. I think one side is quite trivial. So actually this side is trivial. Why? So let's assume that we have some this kind of matrix representation and just mapping 0 to 0 in any field and 1 to 1 and minus 1 to 1. Then still subdeterminant is 0 or plus minus 1. So this is trivial. But quite shocking fact is also we have the other side. And more surprising thing is this condition is restricted only for the binary and the ternary field. So if matroid is representable over the field of 2 element and field of 3 element, then it is representable over the whole field. And that's by Todd. And also after that, maybe in 1978, Blunt and Las Orthogonals proved that this is equivalent with the matroid is binary and orientable. And also this implies that this is equivalent with binary and representable over the real field. So orientable means that it can be represented as oriented matroid. So if you want to know what is oriented matroid, then please take the Michael's talk. And actually this is equivalent with this condition. So this is an easy corollary, and so they proved something like this, and this is also funny result. And thus maybe also there is some result about the ternary matroid. So for the case of the ternary matroid, So firstly, Ray announced that he finds all its obstruction, minor obstruction, and after that, Bixby and Seymour wrote a paper independently about that. And in 1996, when I was born, Sample and Little wrote some amazing paper about the matrix representation of the partial field. So all of things, I mean, not except this, all of things are also not this, but many things, many people research about the matroid representation over the field, but they move up to the something broader notion. So what they prove is M is ternary and quaternary. What this means that it is representable over the field of 4 elements. Then this is if and only if it is represented by some matrix over the complex field, such that all its subdeterminant is 0 or the 6th root of unity. So this is what it means is this 6. And this is quite, I mean, this looks very hard to imagine compared to this, but this is true. And yeah. Okay, now I will explain some known result about the even delta-matroid representation. So first one is by Jim Gillan in his PhD thesis. Oh, also same year. What he proved is similar, analog of the thought. So he proved is now I will say uneven delta-matroid is regular. Here regular means that it is represented by some skew-symmetric matrix over R, such that all its principal minor have Papian in 0 or plus minus 1. And what he proved is this is equivalent that this is representable over binary and ternary. Also, this is equivalent that this is representable over all fields.
In the 3 that you wrote there, what was proved about ternary?
So for the case of ternary matroid, people found that matroid is ternary if and only if they found the minor obstruction, which is U25, U35, and Fano duo. But in this talk, what I want to focus on is if matroid is representable over some 2 field, then this is equivalent to some other field. So minor obstruction is not focus. I mean, not topics of this talk. So skip to right. Sorry. Okay, then why not to mention about the also minor obstruction of the even delta-matroid? So only some known result is about this is done by Boucher and Dushan. Maybe in 1991. I cannot remember the year. Wait, I check. Yeah, 1991. They find the obstruction of the binary even delta-matroid. This is M is binary if and only if it has no U24 minor and also no this. Also some you can remember that these are all bases of the U24, and if we add one more basis, empty set, then this is just all minor obstruction of the binary even delta-matroid. And yeah, this is actually almost all known result for the representation of the even delta matroid. And yeah, now I will explain our application of our main result. First one is we reprove Jim Gillen's result. Okay, and the second one is we prove some analogous result for the sample and Whittle. Also, we also did some analogous result for the blend and the last orthogonals. So, okay, let's explain what it is. So, for the second result, what we prove is on even delta matroid M is ternary and quaternary if and only it is represented by some skew-symmetric matrix over the complex field whose all Bartian is 0 or in the 6th root of unity. Okay? Just same formulation as the sample and Whittle's result. And this, now we have some additional condition. So let's define M4 is also 4 whose ground set is 4 element, and these bases are more possible things. M4 looks like this, and you can easily check, oh, this is binary even delta matrix because of this is a representation of this matrix, this even delta matrix. And what we prove is if M has no M4 minor up to twisting, then M is regular if and only it is binary and orientable. Also, there is some concept of oriented even delta matroid, which just generalize the even the oriented matroid, and also this is equivalent with the binary and realizable. Yeah, this is our main application. Okay, so now I need to
realizable over.
Representable over the real field. Or actually, this is generalized for the realizable over any ordered field.
So when you have this restriction that M has no M4 minor,
Yeah.
So what is the meaning? How should I understand? So can you remove it, or is there what's
So I think maybe we can remove it, but okay, it is worth to emphasize what is this class of the even delta matroid without M4. So this is the class of the even delta matroid, and yeah, this is the class of the matroid or the up to twisting. And M4 minor is something looks like this. So something in between. This is by Dushan. What he proved is on even delta matroid is a matroid up to twisting if and only if it has no M3 minor, which looks like this. And since M3 is a minor of M4, matroid is a subclass of this. So, yeah, so our result also implies the result of the blend and the last orthogonals. And also, if you only restrict your focus onto the binary even delta matroid, then actually binary even delta matroid is some equivalent up to a certain notion, equivalent to the graph with the pivot minor relation. And what it is means that you have no K4 minor. Okay. Now I will explain what is orthogonal matrix. After half of the talk, I will explain what is the definition of the orthogonal. So it is very easy. So there is a reason why I skip. So let M be an even delta matrix. And then the Lagrangian orthogonal matroid is just nothing but a pair. Such that so I mean, for simplicity, I just dropped the prefix Lagrangian. So orthogonal matroid or Lagrangian orthogonal matroid is nothing but just double the ground set. So this means that you also not 1 to n, you also have the 1 star to n star. And then we want to make the basis of the orthogonal matroid have all cardinality n. So for example, so you have let's consider the n is equal to the root 2, 3. Just matroid, which is also an even delta matroid, which is looks like its bases are 1, 2, 1, 3, and 2, 3. Okay. Then its ground set is the corresponding orthogonal matroid has ground set 1, 2, 3, and 1 star, 2 star, 3 star. And its bases are 1, 2, and 3 star. If you're missing some number, then you add it and with a star. And 1, 3, 2 star. So 1, 2 star, 3, and 1 star, 2, 3. And in this sense, you can easily define the circuit of orthogonal matroid. So because of the basis of the even delta matroid doesn't have the difference cardinality, it is hard to define the circuit. But in this sense, you can imagine very simply.
So does orthogonal matroid have their own axiom or the definition?
Yeah, you can make, of course, own definition from this, but
Yeah.
I will only you can
Okay,
simply
alright.
imagine. And or also this is sometimes called the symmetric method, even symmetric method, which named by Boucher. And sub-transversal is a subset of its ground set such that it does not contain any I and I star simultaneously. And a transversal is nothing but a subtransversal whose size is n. So in this case, you can check that all bases of the orthogonal matrices are transversal when n is equal to 3. And now I will define what is circuit. A circuit is also a subset of the ground set, and moreover, it's not a subset. It is a minimal subtransversal such that it is not contained in any basis. So in this setting, we always, in the case of the matroid, you only consider about the just sets or minimal subsets, but in this setting, we only consider about the subtransversal. So bases are also subtransversal and circuits are subtransversal. Minimal subtransversal, not containing the basis. So, okay, this is some setup.
So the elements of B prime is called the base?
Yeah,
Basis.
the element of this is called the basis or base, and yeah, the circuit are defined in this way. Maybe I will not use the circuit anymore, but just I want to emphasize. Then I will explain our main result.
Probably minimum non-empty subtransversal.
No, you don't need. Sorry,
You don't need?
because of this condition, empty set is always contained in the basis, right?
Yeah.
That's right. But when we define the chain group, a chain group's representation, we need something like that. But yeah. So our main result. Also, I think you were quite surprised about that. Until now, I didn't define what is trade is, but I will define it later. Sorry. So what it did is, the first, we define some generalized concept. For matrix representation. And the chain group representation. Chain group representation is nothing but a row space of the disk for the matrix in the matrix representation. And also some vector action or covector action. It maybe comes from the oriented matrix. And this is defined for the orthogonal matroid over a tract. So for the case of the matrix generalized concept of the matrix representation, we call it orthogonal when given tract is F. Orthogonal F matroid. And for the chain group representation, we define some two concepts. The first one is orthogonal F signatures, and the other concept is F circuit sets of some orthogonal matroid. And the remaining concept is orthogonal F vector set. So this looks weird, but I will also give some example. So how our concept generalized the previous known concept. The first one is orthogonal K matroid. Here K is the sum which is called the Krasner hyperfield, which consists with the only two elements, 0 and non-zero. And it captures that always non-zero plus non-zero can be a 0. It captures certain kind of this kind of problem. And this is nothing but equivalent with the just no ordinary orthogonal method. And if f is k, f is a field, then orthogonal f matroid is nothing but a just usual matrix representation or the chain group representation of the orthogonal matroid. It's the same. And if f is something like sine hyperfield or the tropical hyperfield, it corresponds to the oriented orthogonal matroid or the tropical with vector set, which this is defined by Wenzel, and the other thing is defined by Lincoln. And this is something in the 90s, and this is done in the 80s. Yeah, so what I want to emphasize, our concept generalizes in lots of concepts. Also, if we restrict orthogonal K matroid to a certain kind of orthogonal matroid, then with certain properties, naturally, the matroids comes from the orthogonal matroid naturally by considering all bases have the sign cardinality. So if we consider some corresponding concept, then this is equivalent with the F matroid, which is defined by Baker and Bohler. So I think I forget to mention this paper. So I think this paper is very important. So our work is inspired by this paper, which name is Matroid over the partial hyperstructure. Here, partial hyperstructure is nothing but a tract. Okay. The second one is we show that the cryptomorphism. So what it showed is all these four concepts are equivalent in the strong sense. Also, we define it as a weaker sense, but they are not equivalent. Only some of them are equivalent. But in the strong sense, they all are equivalent. So this, yeah. And the third one is, maybe this is most important with respect to the application. So what it did is representability or orthogonal network is related with the properties of the tract. So what properties mean in here is something like morphism of the homomorphism of the tracts and also categorical product of the tract. So this is highly related with the representation of the even delta matrix. So I will introduce this proposition. So okay. Still, I didn't define what is tract and what is morphism, but let's assume there is some tract and which has some morphism between them. And M is an orthogonal matroid which is representable over the F1. And then what we have is M is also representable over F2. So this, which looks quite natural. And the second one is also we have orthogonal matroid which is representable over both F1 and F2. Then this is representable over its categorical product. Okay, to understand your help, I will cheat a little bit. So here we have, and so this theorem means that we have an orthogonal matroid which is representable over the both ternary field and the quaternary field. Then this is represented by this kind of special form of the matroid, special form of the matrix. And what it has is, by definition, this is equivalent with this is representable over the certain height of it, which you usually call the 6th root of the unity partial field. And because this structure is, the product of the F3 and F4 is isomorphic to the R6, the 6th root of the unity partial field, that comes directly. So, okay, I will explain this one more later, but this proposition directly implies the second result. Okay. Fortunately, I still have time to define the track. So if you have any question, then feel free to interrupt. So track is a pair of the abelian group G, and which is written multiplicatively, and some null set NF, which is a subset of the group semi-ring. This is nothing but the collection of the formal sums. So maybe the abelian group. I emphasize that G is written multiplicatively. So this G gives some multiplicative structure, and NF captures some additive structures, and which satisfying overall certain axioms. So first,
So can you say what N of G? So G is abelian group.
yeah, G is an abelian group, and this is N, natural number, and G is just sum of the sum of the formal sums of the elements of the G. So actually in G we didn't define the addition yet, but yeah. This
Oh, so addition is not defined in abelian group, I see. It's
Yeah.
for multiplication.
yeah, this is with the multiplication.
Oh, I see.
So sometimes people use this notation, because this corresponding to the non-zero elements of the track. And the first condition is 0 in G in the group semi-ring is in the null set. So of course null means 0, so 0 is in the 0 set. Right? Null means 0 in maybe in German?
Okay.
No?
Sorry, I wasn't listening.
0 is null is 0 in German?
Yeah.
Okay. And the identity element of the abelian group is not in the null set. And the third one is there exists unique elements, actually which behave like a -1, such that one. I will skip G. So epsilon is in the null set.
So epsilon is a subset, an element of something, or
I'm sorry.
is epsilon?
Epsilon is in the G. Thank you. And the last condition is some also trivial condition. So we have G and some sums which sums to be 0, then of course its multiplication by 0 is in the null set. So actually, epsilon, you can understand epsilon as a minus 1 in some sense. And even this here in here, we didn't define the minus here, only we do addition, not the inverse. And from the first and the not first, from the second and the third condition, you can easily get the for any you collect any element of G, then it is not in the null set. Okay. So G is something a set of the non-zero elements, and from the second, third, and the fourth axioms, you can get the epsilon square is 1, because if we know that 1 plus epsilon is in the NF, and because of this, you can directly this, right? Oh, sorry. So you have 1 plus epsilon is in the null set. So 1 plus minus 1 is in the null set. And if you consider the epsilon, epsilon, then epsilon plus epsilon square is in the null set, and because of this axiom, this must be 1.
How do you think the last one?
Last
implication.
So because of that, this implies this. This there is unique. So maybe we need.
Oh, I see. So epsilon.
But what does epsilon times now mean? Epsilon is nothing in. No, epsilon isn't.
Epsilon is in the
right.
just element of the element.
Right.
But I mean, that says that epsilon is unique element, so that 1 plus epsilon is in NF. But now, epsilon square plus epsilon is in NF. And does that mean
Plus is nothing in.
Maybe some more step needed? I'm confused, sorry.
Can't we just multiply the inverse of epsilon?
Inverse of epsilon?
In G.
Then inverse of epsilon
Plus is nothing, so that is.
plus 1 is in
Plus
here.
in
So
G.
this means that epsilon is equal to epsilon. Oh, yeah, you're right. Yeah.
Oh.
Yeah, thank
Oh,
you.
multiplying epsilon inverse.
Right.
Thank you. You're right. And some another
I
thing is
see.
x, y is in the this, and x plus, if we know that x plus y is in the null set, then what you know is y is just epsilon x. So we can abbreviate this as a minus x. Now I will give some examples of the tract. And if I have enough time, then maybe I will try to prove our application. I explain very roughly, but if I have time, then I will explain a little bit. This is just 3-line proof. So one typical example is, of course, a field. So let's consider a field K. And from this, we can construct some corresponding tract. So so G is the abelian group, multiplicative group of the G, K, and its null set is nothing but the former sums of element in non-zero elements, such that which is 0 in original field K. So let's give some examples. So when K is equal to the binary field, then of course there is unique non-zero element, and its null set is something like 0, and 1 plus 1 is in the 0 in the field, and 1 plus 1 plus 1 plus 1, and 1 plus 1 plus 6 times, or every even time. Okay. And one another example is when this is F3, then you have 1 and minus 1, and you have null set is 0 and 1 plus minus 1. So this is epsilon for this field. And for the binary field, epsilon is just same as the 1. And 1 plus 1 plus 1, and minus 1 plus minus 1 plus minus 1, and so on. Is it okay to type this? And the second example is some hyperfield. So one is the Pesna hyperfield, denoted by you know what it is, mass BB. This has its non-zero element is only there is unique non-zero element. So don't understand this as a 1. This means that non-zero. And so its null set is something like this. So which is equal to the except just 1. So 0 and every sums with at least 2 terms are in the null set. So this comes directly from the real field. So if you assume this real field, and let's divide it into the 2 sets unfairly. Okay. And if you only observe its multiplicative group, then yeah, let's quotient by itself. Then this means that you have the non-zero elements. And in the quotient, we do not consider about the addition. We only consider about the multiplication. But let's consider some addition. And of course, this. If we denote by x, then x plus x might contain 0. So non-zero plus non-zero might be 0. So this captures this. Also, x plus x also contains 0. But x itself does not contain 0. And the other thing is the sign hyperfield, also introduced by Michaels in his talk. Denoted by S, which has 2 elements, plus and minus, and okay, it's hard to write. So 0 is in the null set, and positive plus negative is in the null set, and positive plus negative is in the null set, and so on. So all sums with at least 2 terms, and which contains at least 1 positive and at least 1 negative is in the null set. So also it comes from the real. So in here, yeah. And yeah, its multiplicative group is divided into 2 parts, and this is a subgroup. So let's quotient by this. Then it has 2 elements, which is R plus quotient by R plus and R minus. And yeah, then after that, let's consider this as a plus and this as a minus. Then of course, if you add many positives, then it can be a 0. But if you add 1 positive and 1 negative, then that can be a 0. This captures this kind of properties. And I think I need to, sorry for, maybe I will use just 2 minutes. I need to explain the partial field. So the third example is related with our application is partial field. So the regular partial field, which denoted by this, is nothing but you have the 2 elements, 1 and negative 1, and its null set is 0 and 1 plus minus 1, and 1 plus 1 plus minus 1 plus minus 1 and so on. So 1 and minus 1 appear same time, exactly the same time, and so on. This is regular partial field, and actually the represent, so even delta-matroid or matroid is representable over U0 is equivalent with this is regular. This is easily checked by definition. And another thing corresponding to the sample and Witter's result is the partial field of the sixth root of the unit partial field. Denoted by R6. So its non-zero element is nothing but the sixth root of the unity in the complex numbers. So if I denote the first one is as omega, then its null set consists by 0 and some sums of the powers of the omega, which is 0 in the original field C. Something like that. And yeah, what you know is this is related because of our proposition, and this comes directly implies the central electricity. That's all for my talk, and thank you very much.
Thank you. Maybe you want to mention your cursor?
Didn't I?
I mean, who's
Who is
that?
Who is this?
Who's your co-author?
Yeah. Oh, sorry, I forget. So my cursor is Donggyu in Georgia Tech. So when I practice this talk, I always say this first one. So I'm forget. Sorry, Donggyu.
You're curious, like, who's this guy? Because we never heard it, right?
Yeah, that guy.
Oh, right. Yeah. Right. Any questions?
Could you just show the axioms for the tracts?
Yeah.
So with the examples you showed, it looks like should I be able to also combine like if I know that G1 plus G2 is in the null set. And I know that G3 plus G4 is in the null set. Should I be able to add them all together?
So that's not true for in this definition, but most of tracts what we are interested have this kind of properties.
But it's not part of that you just
this is very broader concept, so this is not true. But most of things, of course, field and partial field and most of the hyperfield what we are interested have this kind of properties.
Are there any ones that people consider which don't satisfy this additional property?
I'm not sure about them. Maybe, I mean, among the interesting one, I don't think so.
Because because you could just have that they all have at most two terms.
At most two terms?
You could have a tract where every formal sum allowed only has two terms. It's only
no, two terms they are not enough sometimes.
But for some example, it would satisfy the definition. There's nothing which forces you to take anything of more than
for the case of the sine hyperfield, two terms information about the two terms is not enough.
It wouldn't be enough for maybe any interesting application. It would just, as far as I can tell, it would still be a tract.
Yeah.
Okay, just check.
Yeah. Okay. But sometimes it is enough to know up to 4 terms or up to 3 terms. This happens only for the partial field. But for the usual case, we need to know the more terms.
Can you move on to different question?
Yeah, sorry.
Yeah.
That's
Yeah.
I have no more questions.
Yeah. So I was wondering about that. You said orthogonal K-matroid is the same as orthogonal matroid.
Yeah, I mean there is some natural bijection. I mean.
So what do you mean by orthogonal K-matroid?
Ah.
Yeah, I don't know the definition.
Sorry, because
So
of
you
the
have tract, but you don't see the what do you mean by the
yeah.
representable over the tract.
To define this, I need to introduce some weird things. So I will assume you are familiar with the Grassmann-Floch relation, and then
Maybe.
I mean
Yeah.
so for the case of the length, so let's go back to the matroid first. Then makes life easy. Make life easier. And length R and matroid on n element. And let's consider the or vector space or n-dimensional vector space of the n-dimensional vector space and the r-dimensional subspace of the n-dimensional vector space. And this is can be understood as a solutions of this projective space. So this is embedded in here in this projective space, and this is exactly of solutions. This is understand exactly solution of the Grassmann-Floch relation, which denoted which is written in multiplicative. Okay, so it has some. So we have some sets of the R plus 1 element, R plus 2 elements, and we have some other sets T with the R minus 1 element, and maybe some R minus 1 element, then let's consider some and our Grassmann-Floch relation looks like this. And this is corresponding to the maybe R plus 1 and R minus 1. So this corresponding to the set of the size R, and this also corresponding to the set of the size R. And we collect all, so this all coordinate of this is indexed by some n R side subset of the n. And then if we collect all non-zero coordinate in this point, so you have this point in here which is satisfying this condition. There is many relations which satisfying this condition. And if we collect the B in R such that XB is non-zero, then this is nothing but a basis of the matroid, some matroid. And this is defined over some certain field K, but if we consider this as some arbitrary tract, then we can replace this condition by it is in the null set. Then also this condition, or maybe you can understand as this is in the Fx. And this condition also gives the matroid, because of this condition can be understood some stronger condition than the basis exchange action, stronger basis exchange action. And since for when F is the Krasner hyperfluid K, then you have only the information at 0 and non-zero. This means that you select this or not select this. Something like, because of that, you can easily say that this K matroid, which defined by not our paper, in the paper of the Baker and Goldor, this is same with the matroid. And yeah, this same happening for the orthogonal matroid. Yes, sorry, this is hard. I mean, because of hard to explanation about the Grassmann. I mean, if I to define this, I need to explain many things. So that's
Other questions?
I mean, is there a way, if you have a hyperfield, to see like what elements would be in the addition, or if the addition is really empty in the partial case? Like, can you recreate the addition operation
Recreation.
from a hyperfield?
What is recreation means here?
Can you deduce?
From
No,
the
work out like what is the, if you have a hyperfield,
Mhm.
can you work out what the hypersum operation is from? Is it nice to write from the?
Yeah, there is way to understand the hyperfield in terms of the tract.
Yeah.
Yeah. But yeah, I cannot remember what is rule exactly. Yeah. But usually, you can understand. Yeah, in the hyperfield, yeah, sums can be. Yeah, there is way. Sorry, but I cannot remember exactly what it is.
Right. Maybe everyone is tired now. So okay, let's thank the speaker again. Thank you.